With this short video, I would like for us to talk about the role that axial groups play in the structure of the chair forms of cyclohexane. And what I have done in this first slide is I have just reminded you what the axial positions are. There are three pointing up, three pointing down, and each carbon has one. Now let's go down to methyl cyclohexane, which we talked about in class on Wednesday. The methyl group can be either axial, that's the first drawing here, or equatorial, which it would get to by doing the ring flip. Remember, an A goes to an E when the cyclohexane flips, or an E goes to an A. The preferred orientation of the methyl group is equatorial, so that the methyl group is not interacting with the axial hydrogens on the 1 and 3 position relative to the methyl group. So the preferred three-dimensional structure of methyl cyclohexane has the methyl group in the equatorial position. Now let's keep that in mind and move to methyl cyclohexanes, or any cyclohexane with two branches or two substituents. Cis 1,2 disubstituted, represented by the methyl, means that the two methyl groups are on adjacent carbons 1, 2, and must both point in the same direction. As a consequence, one must be A and one must be E. We can't do it any other way, because if we made them both A, for example, one would point up, one would point down. Or if we made them both B or both E, one would point up and one would point down. So the correct structure for a cis 1,2 disubstituted cyclohexane is AE. Now the trans is the reverse thinking of that. In this case, we can put the groups pointing in opposite directions, the two methyl groups. One can point down and one can point up, and neither one is in an axial position. So the trans 1,2 disubstituted cyclohexanes will be EE. Now, I want to say something a little bit more about the trans disubstituted, just to remind ourselves of something. We could have thought that the two methyl groups, the two substituents, could be trans and AA, one pointing up and one pointing down. But because of the 1,3 diaxial interactions, that's the hydrogens on the positions 1 and 3, as pointed out in class, to the position where the methyl group is, for example here, and it would interact with the hydrogens 1 and 3 at the top and the bottom, so it would flip to get the methyl groups both equatorial. So even if we considered the trans diaxial orientation for 1,2 disubstituted cyclohexane, it would immediately flip to the diequatorial, and you can see I have the arrow going from left to right much longer than the shorter arrow going from right to left. Okay, now let's think about this same thing with the 1,3 disubstituted. In cis, they have to both point in the same direction, and if we had gone around the ring and put all the A and E bonds in there, we would see that the methyl group on carbon 1 and the methyl group on carbon 3 can both be in equatorial positions. And when that happens, that's the most favored position for the groups. So cis 1,3 disubstituted is diequatorial. Now in the trans, we cannot avoid an axial position for one of the methyl groups, because in order for them to be trans, one will point up, one will point down, and if they're 1,3 related to one another, the carbon number 1 would have an axial methyl. And in order for carbon number 3 to have an equatorial methyl, it would point down. So one of them would be axial, and there's no way to avoid that. So trans 1,3 disubstituted has axial equatorial. Let's look at 1,4. 1,4 is exactly the same as 1,2. If we have the methyl groups on carbons 1 and 4, and we want to think about cis 1,4, we would see that one could be axial and one could be equatorial to accommodate that, or would have to be. There is no other way to have them cis and 1,4 without one of them being an axial position. Now if you look at trans, the equatorial positions 1 and 4 on trans, one points down and one points up, and as a consequence, trans 1,4 disubstituted preferred three-dimensional orientation is going to be di-equatorial. Okay, one final example is, let's look at when the groups are not the same in the disubstituted, and I have the cis 1 tertiary butyl 2 methyl cyclohexane drawn for you on the left. I've put the tertiary butyl group in an axial position and the methyl in an equatorial. They're both pointing up. But because the tertiary butyl is much larger than the methyl group and would have much greater axial interactions on the top face of the cyclohexane, a flip would take place so that the tertiary butyl ends up equatorial and the methyl will now be axial. Remember, we can't avoid one axial and one equatorial in cis 1,2. So as a consequence of that, the tertiary butyl is going to be accommodated better in the equatorial position. And then what we see here now is the preferred three-dimensional structure of the 1 tertiary butyl 2 methyl cyclohexane in the cis stereochemical description or orientation. So I hope you've understood what we've gone through here, and it's been helpful as complementary to the lecture.